the sun. Okay, the sun is a really, really abnormally big star in the grand scheme of things. Okay, most stars out there are really small and faint. They're red dwarfs. Okay, now we don't think of that normally because if you look in the night sky, you don't see very many red dwarfs. Can anyone take a gander, try and take a guess at how many red dwarf stars you can see in the night sky with the naked eye? No binoculars. 0. I heard a 0. Any other guesses? Someone's holding up. Is that a 3? 3? 2? Yeah, those are all good guesses. Yeah, the number is actually 0. You could, I don't know, maybe there's some freaks who have really, really, really good eyesight who might actually be able to see 1. There's 1 that's pretty close to being at the naked eye limit if you're on top of a tall mountain. If you got some freak who had like superhuman vision and you put them on top of a mountaintop in very dry conditions, they might be able to see the 1 brightest M dwarf, okay, the 1 brightest red dwarf. But for the most part, yeah, you can't see a single one of them. Right? And so we don't think of these, it's just like bacteria, right? I mean, by far the most common critters on our planet are single-celled organisms, right? And you know, biologists all know that, and we all learn that in biology class, but we don't think that. Like when people think like to name living creatures, they name like dogs and ponies and humans. They don't name like different kinds of bacteria, and that's because bacteria are just too small. Question?
How can you tell if planets' moons are habitable?
How can you tell if the planets' moons are habitable? In general, moons are less good places than planets for habitability because they're too small. So they suffer from the same problem as Mars, but it's even worse because they're generally too dinky. Yeah, so that's the deal with moons. If you had like a planet the size of Jupiter, in principle, it could have moons like that are about the size of Earth, and so then it could be habitable. So some people have worried about this. There's actually a fellow at Harvard just down the road who's basically been doing this for the last like 4 years. He's been trying to look for moons around giant planets, but so far he hasn't found any. So I don't know. Okay, so stars. So most of those red things there are M dwarfs, which we call red dwarfs. Okay, don't worry about why it's called M. A lot of the terminology in astronomy is super archaic. But just red dwarfs, so they're red stars. And then there's another 12% that are K dwarfs, which is just another kind of red dwarf. Okay, they're a little bit more like orangey red, but they're still basically redder, fainter, smaller than the sun. All right. So then you get to the sun-like stars, and so there's almost 8% of stars out there are like the sun. Okay, so we're definitely in the minority. Right? Most of the stars out there are not like the sun. Most of them are smaller, they're fainter, they're redder. Okay, that's all I wanted to tell you here. Any questions about stars?
Do red dwarfs have habitable zones?
Yeah, they sure do. And you know what's convenient about a red dwarf habitable zone is that because the star is so small and faint, the habitable zone isn't super close because the star is really dinky. So if you want to stay warm, you have to huddle in close to it, right? So it's like if you have a really crummy fireplace, everyone's kind of huddled around trying to stay warm. So for for the sun, the habitable zone is basically where the Earth is, right? So it takes us about a year to go around one orbit. But if you're in the habitable zone of a red dwarf, sometimes you go around your star in like a week or a month. Okay, so it's much closer into the star. Yeah?
What percentage of stars are binary systems?
Most of them. And we tend to ignore that because it makes all of our lives more complicated. But yeah, most stars out there, so if you look in the night sky, basically half of the dots that you see as a single star is actually a binary system. So if you do some math in your head, that means 2/3 of stars are in binary systems.
Including red dwarfs?
Yeah, well, so this is an area of active research. Exactly what the binary fraction is a function of stellar mass. And so it actually varies as a function of stellar mass. So for example, high mass stars, the really blue ones, you tend to get binaries and they tend to be twins. They're like identical copies of each other. And I think that's less true at the red dwarfs, but I don't know the exact fraction.
Right.
Yeah.
As I understand, lately there's been some speculation on whether a couple of red dwarfs that are fairly close to Earth, one of them Proxima Centauri, the other one, Gliese 7c, could have habitable zones and therefore habitable planets. Any thoughts on that?
Yeah, so the question is about a few specific M dwarfs and whether they have habitable planets. Yeah, I mean, there's plenty of planets that have been discovered in or near the habitable zones of all sorts of M dwarfs. And so at this point, it's not really newsworthy. I guess it's still pretty cool, right? To find a planet that's like habitable is still pretty cool. There's a couple years ago where it was like a really big deal, and one guy named one after his wife, and then that turned out disastrously because it turned out the planet he discovered named after his wife didn't actually exist. It was just kind of like it was noise in the detector, so that was kind of offensive. So there's a moral there, which you can keep in the back of your head. But yeah, I mean, nowadays it's not terribly special to find a planet that's in the habitable zone of its star. In fact, boom. Okay, here's the answer to your question in a statistical sense. Okay, and so there's another histogram, right? And the green zone there is a habitable zone. And so the number of planets per star. Okay, there's enormous uncertainties on it, but the point is, and this is a result from folks over at Harvard. This is Courtney Dressing's work, and so the basic number is something like 15% of red dwarfs have a habitable rocky planet, or like it's got a rocky planet in the habitable zone. All right, and there's gajillions of red dwarf stars, and so there's tens and hundreds of millions of habitable planets in our Milky Way galaxy.
Quite close.
What's that?
Well, Proxima Centauri is quite close.
Yeah. So obviously the ones we would love the most would be the nearby ones. Yeah, and that's generally the case because those are frankly the only ones we can actually detect well, are the nearby planets. And then if we want to characterize them, like we want to actually go and measure their temperatures directly, which I may or may not get to tonight, then you really want them to be nearby. So our favorite planets are always the nearby ones. So I always tell people my favorite planets are the ones that have like Arabic names, because those are the ones that were named during the heyday of astronomy in the Middle East, right? And so those are like really bright stars. Things like Betelgeuse or Aldebaran or whatever. I mean, those are like, if you found a planet around one of those stars, you'd be a very happy person, because everyone could just like point at the star and see it. You won't be able to see the planet, but even a modest-sized telescope would be able to get useful data on that planet. The next most useful planets are what I call dead white guy stars. So they're stars named after some dead white guy who probably was rich and paid a lot of money and got stars named after him. So like Henry Draper is a classic one. There's a lot of stars that are like HD for Henry Draper and then a bunch of numbers afterwards. And it's basically because he gave a lot of money to Harvard, and he had a bunch of women go and do a bunch of astronomy to learn all this stuff about stars, and all the stars were named after him. So Henry Draper stars are pretty good, because back then they had kind of crummy telescopes, so they couldn't see very far into space. So they saw only the brightest stars. The worst stars are stars that you've never heard of before. That like the first person who ever discovers a star is the person who finds a planet around it. That's basically worthless, because you found a planet orbiting a star so far away that even the biggest telescopes on Earth can barely say anything about it. There's a question back there, young lady. What is the closest planet to our solar system? That's like outside of our solar system, I assume, because otherwise I'd cheat and say Earth. So there's a planet around Alpha Cen, so Alpha Centauri, right? So that's like a triple star system. There's a planet there. It's not a planet you'd want to live on. It's like a rocky planet, so far so good, right? It's made out of the same stuff as us, but it orbits around its star about every day or so. So it's like super, super close to its star. It's like boiling hot. It probably has like lava on the day side. The day side is probably all lava, so it's not a good place to live. But yeah, so that's the nearest planet. Question? Okay.
How long do red dwarfs live compared to our sun?
They live basically forever. So a red dwarf has never died in our universe. Yeah, they live for like 50 billion years, 100 billion years. Yeah, so that's another convenient thing about red dwarfs, is not only do they have this like really cozy habitable zone, it's that they live forever and they barely get brighter during their lifetime. So they're like really solid, good place to go look for life. Guess I want to, in my last 5 minutes, I'm just gonna hit you with one last nugget that you should keep in the back of your head, is that we should not just believe this idea of this habitable zone, okay, which is based on computer simulations of what we think climate does All right, and so instead of taking that at face value, we can actually go out and measure the temperatures of planets. All right, and so we do this exactly the way that modern day people measure the temperatures of their babies with the infrared, right? You have your little IR gun and you zap their forehead and it measures infrared radiation coming off their forehead, right? Well, it turns out this is my thermometer. It's the Spitzer Space Telescope. Okay, it's a very expensive thermometer because it's out in space. It's not even orbiting the Earth, it's orbiting the sun, so it's like really far from the Earth actually, which is good because the Earth is kind of warm, so you want to be really far from the Earth if you want a really, really accurate thermometer. And so what we do is we take this thermometer and we point it at a star that we know has a planet orbiting it. And what we see is not what this movie is showing. This is an artist's rendition. Okay, what we see is going to be shown like on an inset plot here. All right, so when the planet passes behind the star, we get a little brief dip in brightness. Okay, and that brief dip in brightness is telling us something about how bright the day side of the planet is, how hot the day side of the planet is compared to the temperature of the star. So again, people have been studying stars for a really long time. We know how hot the star is, and so now we've actually just measured the temperature of the planet. All right, and so here is a bunch of planets. So I've got Mercury as a little dot, as a little gray thing, and then Earth. Okay, and then the x-axis is basically how much sunlight is hitting the planet, and the y-axis is how hot the planet is. And so it's sort of comforting that planets that receive an awful lot of sunlight are hotter. It doesn't have to be that way. Okay, it depends on how cloudy they are, but it turns out they kind of follow this trend. But the key thing here is that each of these dots is an actual world out there. That's a planet where we can actually measure its temperature, right? And so the first step for this question of habitability is, taking the theorist's word for it, right? People who really understand climate tell us, yeah, this planet should be habitable. But we don't want to take the word for it forever, right? So what we're doing now is going out and actually measuring the temperatures of planets. And as you can see, most of these planets are really, really hot, right? Their dayside temperatures are like thousands of degrees. Well, I have it in Kelvin, but if I put it in any other units, it would still be thousands of degrees. It doesn't matter. It's really, really hot. It's hotter than your oven, all right? But that's just because those are the ones that are easiest to look at, right? The stuff on the bottom part of the plot, we need something bigger than Spitzer. We need a bigger infrared telescope, and thankfully NASA's launching one. And so stay tuned because during the next decade, all right, because it's going to launch in a few years. So in the next decade, we should be able to measure the temperatures of not just these ridiculously hot things, but also planets that are more small and temperate, that are more Earth-like. And we can actually not just say, yeah, this is in the habitable zone, but then we can go and check. We can look at its temperature and figure out, okay, does this planet actually look habitable upon closer inspection? So with that, I think I'm just going to take any more questions you guys have. Thank you. Wait, maybe the guy with the mustache first.
Can you touch on orbit, red dwarf, and rotation of the planet? Is it possible that you simply always see one side, one hot, one cold?
Yes. The basic answer, oh yeah, okay, so the question, for those of you who didn't hear it, is how, okay, if you have a planet orbiting really close to a star, it gets into this funny thing called being tidally locked, which sounds crazy, but you're all familiar with it, because when you look at the moon, well, those of you who actually pay attention, if you look at the moon, you'll notice you always see the same side of the moon, right? You're always seeing the exact same side of the moon. The first time that people saw the far side of the moon is when the Soviets, went over to the far side, and that's why everything on the back side of the moon all has completely different sounding names than everything on the front side, because the front side was all named by Galileo and friends, and the back side is all named by Cold War era Soviet scientists. And so that's called tidal locking, the fact that the moon always keeps the same side facing us. And this is generically what happens when you have an object orbiting very close to another massive object. So if you have a planet orbiting near a red dwarf star, if it's in really close to stay warm, it'll tend to be tidally locked. It'll have a permanent day side and night side. So in case that freaks you out a little bit, know a couple things. One, it's not that bad, so we can run climate simulations on these planets, and we know that the climate is not terrible. The night side conditions are actually quite temperate. The day side conditions aren't too hot. The day sides on one of these planets would be sort of like our tropics, so it'd be kind of overcast and rainy. It'd be like a tropical rainforest on Earth. And the night side would be clear, kind of cool. It'd be great, right? It'd be like having your night in the Southwest in the US, right? Kind of cold, dry, clear skies, good for astronomy. Except unfortunately the sun never comes up. So yeah, so that's the deal with those stars.
Your answer about climate change led to a debate at our table. So the debate is, were you saying that the climate change would be not enough to boil the oceans, but enough to affect living beings? Or were you saying that you didn't believe it would have an impact on life?
I was saying it's enough to have an impact on human beings, well, and obviously other life forms on our planet. Yeah, but not enough to boil away the oceans. Yeah, I mean, I'm sure some critters could survive, even if we start boiling away the oceans. There'd be some critters that could probably survive that too. But I think at this point we've already killed off enough species that I think we have evidence that humans are pretty good at that too. Oh wait, there's someone. Was there someone? Oh, young lady. The hottest planet in our solar system is Mercury. Yeah, Mercury orbits the closest to our sun. But the funny thing is about Mercury, here, let me go back a couple. I can do this. Unless my, here, what? Well, okay, whatever. My computer's spazzing out. Suffice to say, most of the planets that we've discovered around other stars are actually far hotter than Jupiter is, than Mercury. Yeah. So Mercury is the hottest thing we happen to have in our solar system, but our solar system is sort of abnormal that we don't have anything closer in than Mercury, because most solar systems out there actually have a whole bunch of planets, not just like one planet in closer than Mercury, but they have like 4 planets interior to Mercury that are really hot. So yeah, it's,
okay, so who knows? Maybe 2 more questions?
Yes, you.
So just a question on that. I thought that Venus was hottest because it had an atmosphere between each, not so, and Mercury doesn't.
Yeah, sorry. Yeah, at the surface, Venus is hotter. The temperatures that we can measure for exoplanets are all based on the emitting temperature. So if you looked at Earth, for example, it'd be like 255 Kelvin. It's really cold. It'd be like the temperature of the top of Mount Everest or something. It's the temperature from which infrared light actually goes off into space. So it's the temperature high up in the atmosphere. So if you look at that temperature, if you look at Venus at that temperature, at that level, it looks quite cold, actually, because it's very cloudy. And so, yeah, you're quite right. At the surface of the planet, then Venus is hotter. By that argument, you could say that the very hottest thing would be you just go down deep enough on Jupiter, right? It keeps getting hotter and hotter. There's no surface, right? So if you go deep enough on Jupiter, you're going to get ridiculously high temperatures. So it's sort of that's kind of a fuzzy definition, I guess. All the way in the back.
So you said that no matter what we do, the maximum part, sort of the maximum part we can do is about 5 degrees. I want to know what's the range of temperature that would be enough to take this feedback loop. You said that it's just going to get worse after that, and there would be a catastrophic failure.
Okay, so how far would we have to kind of heat up Earth to get into a runaway greenhouse? Is that the question? Yeah, people are still debating it. I mean, there have been papers in Science and Nature in the last couple of years trying to figure this out, and it basically depends on the details of your model. So we don't quite know, but basically some people say that we're actually kind of close to it, which means that so these are the people that say that maybe humans could trigger it in like a complete nightmare scenario where all the glaciers and everything melt away, then maybe humans could trigger it. And other people say no, like you'd have to move the sun in by like 10% or something closer to the, which is like an incredible amount of radiative forcing. So we're not going to do that. Like unless we go out of our way to screw up the planet, we're not going to do that. Okay, in the back.
So, since red dwarfs are smaller and they can weigh less, does that make it easier to detect planets in the red dwarf system?
It sure does. Yeah, so that's why I can actually tell you that something like, every red dwarf, roughly speaking, every red dwarf out there has a planet that's rocky and it's in its habitable zone. All right, so for every star, there's about one habitable, temperate, kind of rocky planet. I can't tell you that number for sun-like stars yet, because those planets are harder to detect, because the stars are bigger and they're harder to move around. And so we don't know how common Earth twins are, but we do know that most of the habitable planets in the universe are probably orbiting red dwarfs. Is there a larger what?
Habitable zone.
No, it's actually physically it's smaller in space. You have to think in log space for this to make sense, but it's the habitable zone is physically smaller in terms of like kilometers, but in a relative sense it's wide. Don't worry about it.
So we're well over time, so everyone please thank Nick Cowan again.